All right, good afternoon, everybody. My name is Mark Laesch. I'm from Baker Industries, Lincoln Electric Company, and I'm here to talk to you about large-scale additive manufacturing. All right, I started at Baker about 7 years ago. My first role there, I was a program manager. My job directly was related to aerospace tooling and processing of tools, getting our departments kicked off, getting materials ordered, launching our fab shop, our machine shop, our build and inspection departments into fabricating tools to the GD&T tolerances on the prints and also to the models. From there, I've evolved into several other roles, including being in charge of our design department, the program management group as a whole, and now I'm into more of an operations role. Throughout that, I've had the opportunity to work in everything from aerospace, obviously, defense, energy, power generation, oil and gas, you name it, I've probably done something with it, so it's been very exciting. Lincoln Electric, we are a global manufacturer and market leader in engineering, design, and manufacturing. We cover everything from arc welding solutions to oxy-fuel cutting equipment, leading global position, brazing and soldering alloys, founded in 1895. A very, very large company. We are present in over 160 countries around the world and have 11,000 employees globally. Baker Industries, this is where I'm located at. It's up in Macomb, Michigan. So we are a tier 1 supplier of larger scale tooling, prototypes, CNC machining. We were founded back in 1992. We were a 3-person shop. One of those employees is actually still employed with us. He is our machine shop manager, Bill Edney. He could not be here today, but Bill's fantastic. We've now grown from 1 building back in 92 to 5 buildings, and we have over 250,000 square feet state-of-the-art manufacturing space, spread across, about, I don't know, it's a half mile apart from all the buildings. We were a very early investor and adopter into 5-axis CNC machining, and as well as the additive manufacturing technologies. At a much smaller scale early on, now we've grown to a much, much larger. Back in 2019, we were acquired by Lincoln Electric as part of the company's $600 million automation and metal additive manufacturing business. And that's a question that we get a lot. Is Lincoln Electric, the people that make the welders? Yes, those are the same guys. They make the weld wire, they make the welders, but they had a much, much larger plan that we're extremely excited to be a part of with them. Large format metal additive manufacturing. What do we mean by large format? We mean direct energy deposition. That's one of the most common ones that we see now. So that's gas metal arc welding. We will refer to it as WAM. You also have plasma arc, you have laser, you have electron beam, and then the other ones that are still out there, cold, solid state. You have cold spray, you have ultrasonic and vibration, and you have friction stir welding. WAM, which is what you're gonna hear a lot of today. We are using this capability that we have generated to completely take over the market and provide something to our customers that I don't think anybody else can. With our technology and with our history and with our experience, we've been able to take our WAM, our proprietary WAM process, and apply it in ways that others can't. So we actually can build parts in atmospheric conditions using our multi-axis rollback technology. We have our own software called Sculpt Print, so we are not working with SolidWorks or CATIA or someone else. It is our own software. So it's not an extension that has to be bought. We get to control all of that. We also, because we're Lincoln Electric, we get to draw our own weld wire. So that's something that's really exciting for our customers. We've been faced with challenges and opportunities where someone's come to us and said, hey, I want to make this out of a certain type of material, but I want something else added to it. So we can actually take that, draw the weld wire for them, add different chemical compositions. If they're trying to get a certain material or a certain composition out of it, we can aid in that production as well. As far as harnessing Lincoln's core expertise, I've kind of already touched on it. I don't think you're gonna find somebody else that is well vertically integrated as we are. From over 100 years of actually making weld wire and having the deposition know-how and the metallurgy history, we've been able to make weld wire, move that into our Sculpt Print OS, move it into our automation systems that we make and supply all over the world. And now with Baker Industries being a part of this team as well, we have our post-print machining and fabrication available as well. Cleveland, Ohio, this is where our headquarters is at. The Additive Solution facility is about 6 minutes down the road in Euclid, Ohio. They've got 75,000 square feet of facility open. There's 18 cells available for print 24/7. And I think they've only used about a third of the building. So I think the plan is actually to go up to 60 weld cells in that facility itself. As far as the envelope size for our printing, this is something that we stand out when we look at some of our competitors and some of the people that are here today. So we have two options when we're printing. So down in the lower right corner of that picture, you will see a robotic arm there. On the floor, we have a floor plate. Just to the left, we have a positioner table. So we have two build envelope sizes up there. The first bullet point, we have an approximate build volume of 4 by 5 by 7 feet. We say approximate because I know we like to push that. We've had some programs and projects that we've actually built up to as far as 8 feet tall. And that's part of what we do is we push our own boundaries to see how far we can go. With the positioner, which is located just to the left in there, this is a positioner arm, and we've got some neat videos we'll share with you shortly that will actually move with the robot and the torch to always keep the welding in 1G. So we're always welding in 1G, and we're not fighting any sort of sag, any sort of deformation to the part that's not required. Now, when we're printing on the positioner, we can go up to 3,500 pounds. We've gone a little bit over and pushed that. On the floor, we're 8,000 pounds plus. So definitely a huge advantage there. Wire feed. So our wire facility is located in Mentor, Ohio. It's about 16 miles or 20 minutes away from Cleveland. So again, not too far. And this is the benefit of being part of this Lincoln family, is that when we need wire, we draw our own. We can run down the street and say, hey, we need more of this, please draw it for us. We're not waiting on a separate vendor. We're not trying to place an order somewhere else. We already have the wire available. So when we talk about lead times and getting you additively manufactured parts and tools quicker, we truly mean it. Along with the Mentor, Ohio plant, which is producing up to 1 million pounds of wire a day, we have the Cleveland, Ohio manufacturing plant. Their output is about 8 million pounds a year. So they are just cranking through wire. I touched on this a little bit early on when we talked about how vertically integrated we are. We have our own proprietary Sculpt Print OS software, which utilizes voxels for slicing and path planning, which allows us to incorporate cutting edge features, looking at non-planar printing and dynamic adaptive bead widths. So this is something that nobody else has. So if you want something printed the right way, if you want us to go through and work with you on your part, work with you on your tool, give you adaptive feedback on the spot, this is definitely the way that you'd want to go. Designing for additive. There's so many benefits when you're looking at your project and your tool and your part and why you want to design and use additive. Lighter weight, you have reduced material usage, part consolidation, less machining. You can use multi-materials in some cases. With Sculpt Print, this is a great example of, now this video is sped up, so I don't want anyone to get the impression that we can actually print that fast, but it is sped up, but this is a great example of how you're actually seeing that positioner arm move in sync with the torch and the robotic arm, so that we contain and we maintain that in 1G the entire time. So you can print this hollow and save on weight. You could print it solid, but this is completely different than the way you would try to manufacture this otherwise. I mean, if you were to actually think about this, you'd either be welding or trying to chip form or bump form 4 different blades on a round slug and try to weld them together, or you're looking at a casting, or you're looking at a forging. You're looking at multiple rounds of testings of those forgings and castings. Where with this, we're able to design this and go to print almost immediately. There's no lag time for the schedule. And then printing this, you're looking at getting this printed within weeks all of a sudden. You're not looking at months or years. This is something that's pretty fun. Scott, you actually did an excellent job, if you're still in here, previously talking about additive and subtractive manufacturing. This is something we worked with at Oak Ridge National Labs. This is called Medusa. So this is our 3-headed monster here, but we've got 3 torches here that are welding, and we are looking to rapidly attack the market and show how much we can deposit within an hour. So this is going to put us more in the range of 15 to 30 pounds an hour of material deposition. Metals that we can print. So one of the most common ones that we do, mild steel, high strength steel, that's a pretty common one. We're extremely competitive with lead time and pricing on those. We see that a lot from our customers. Stainless steels, we can do 316 stainless, 17.4, 410 as well. The nickel alloys, for any of the aerospace people out there, we do have the Inconels available and ready for you. 625, 718, and Invar. Invar is becoming extremely popular now, especially with everything that's going on overseas, with the availability of nickel This is something where we stand out, being Lincoln Electric, is that we draw our own green rod down, we have our own wire. So we have not really been affected as much as some of the other companies have been. So that's another benefit of having that tool within our family. In development right now, we're looking at some ferritic steel. Titanium is kind of an R&D project right now, but still trying. Super duplex stainless, Hastelloy, aluminum, copper, nickel, nickel, aluminum, bronze, aluminum, bronze. One of the other parts of manufacturing that we've kind of broken into that we've seen a really, really big draw has been oil and gas. So a really awesome accomplishment for our team was working on the Section 9 welding code. They actually passed the code qualifying for WAM technology to be used. So we were able to do that with low carbon steel, nickel alloy 617, 316, and 410. And we've been able to produce replacement parts for oil and gas in a much, much faster lead time than them waiting on forgings, waiting on castings, and really holding up production, really having downtime that's unnecessary. Electro power research, we've done a lot of 316 for that. We've also passed through the testing 4,000 PSI of hydrostatic pressure for 1 hour at Stress Engineering Services. So a lot of what we see when we're doing any type of printing is there's additional testing that goes on without. We're not just printing metals and just shipping this stuff out to our customers. We're going through all of the chemical composition, all of the tensile strength testing, all of the fatigue testing. So it's something that we're excited to share a lot of that with our customers and with people that are interested as well. Considerations for large format additive manufacturing. Material selection is one. Geometry and complexity, surface finish and resolution, dimensional control. These are all things that additive manufacturing, when you look at it from the beginning, and again, I can't thank Scott enough for setting me up for his previous presentation, but having the preform and knowing where you need to add machine stock to remove it from subtractively and taking advantage of that at a design phase is way better. It saves you time and money in the long run. So this was a neat project here. This is kind of showing you a comparison between a tool steel block on the left-hand side after it's been run through. Laser hot wire margining steel has been deposited or additively added after the fact. And the example down here, we were challenging weld crack free and what to do, and this was the wear after about 70,000 shots, over double the first run life. So another excellent example of that. Geometry and complexity. We get this question a lot. We've got customers that come to us and they say, hey, I want you to print this. And we go, well, that's a flat plate. I'm not gonna print you a flat plate. Where additive manufacturing comes in the most is when you have complex shapes. You have something that you wanna get near net or close to and leave enough stock so that you can fit your piece within and machine away. So there are times that additive manufacturing doesn't quite make sense. But the times that it does, we want drastic shapes, something that's more complex. If you want cooling channels in there, if you want hollow pieces in there, that kind of thing, it is a perfect solution for that. Surface finish and resolution. So down on the left-hand side, you'll see all of the different AM processes that are pretty common. You're gonna see a lot of them here this week or today. Down at the bottom, you'll see the GMAL or the WAM. This is where we play in. So the good thing to look at is right over here, 5 to 15 pounds per hour for deposition rate. This is something that puts us ahead of our competitors. Not only that, but then when you start looking at some of these other ones like high power laser, they're looking at 1 to 5 deposition rates. Well, unfortunately, for all of the ones that I've seen, our envelope size is larger as well. So that's where we just stand out when it comes to the deposition and getting larger parts out. Dimensional control. This is something that the additive group has spent a lot of time on. In all of our weld cells, they're atmospherically controlled. We have a robot and a torch on there. At the end of the torch, we actually have sensors that are actually taking the surface temperature. They have coordinate systems on there, so we know that if there is an issue during a print, we know what layer it was in, we know what temperature the part was, we know what temperature it was inside of the cell, so that we're constantly feeding information back to Sculpt Print, so it knows whether it needs to pause for 30 seconds, 45 seconds before it goes and lays down the next pass. So if we aren't controlling those variables and you don't have a good process in place and you're not executing, it can get out of hand extremely quickly. Capturing AM benefits with new designs or redesigns. So this is something that we've looked a lot into and a lot of people have come to us. for solutions on is, hey, I have this current part. How do you help me make it lighter? What can we do differently with it? So down in the bottom left corner, this is a great example from Siemens. It's a generative design. So you can see the difference of where the part was to what we're able to put it into. We've got cooling channels, and then in the right-hand side, this was actually a study and a test that was done by the University of Michigan. Secondary processes, so this is where Baker Industries kind of jumped into the Lincoln family as we got acquired with them. We have large and extensive machining capabilities. We have over 35 machines that are 3 and 5 axis. We are very well used to handling profile tolerances being machined within 5 thousandths. Our machine shop alone is 60,000 square feet. And as you've seen in a lot of these pictures, and even in some of the other presentations today, with the WAM, additive manufacturing, the surface itself will look rope-like. It has some striations, and it's not the perfect profile. So you can't take that rope-like structure and make it a profile of 10 or hold your surface without subtractive manufacturing or machining it away. So that's where some of our experience from aerospace tooling comes into work with our additive team, and we put out fantastic tools. Fabrication, assembly, because we've been doing this for so long and we have all of these buildings and all of these resources on hand, we have another 155,000 square feet of assembly, fabrication, weld to support any other of your tooling needs. At Baker and down at Euclid, we actually have ferro arms, we have ferro laser trackers, we have CMMs, and a lot of times we are doing scans during the print process, after the print process, to verify, how close our print was to nominal CAD. We're fitting tools, we're getting everything prepared. Along with that, I touched on a little bit, but there's additional testing processes that often get performed. So we've had test coupons that have gotten printed onto some of the face sheets and some of the parts and tools we've done. They've actually carried out with those face sheets to go through, whether it be a stress relief, they've then gone to tensile strength testing, elongation testing, anything else that may be required, and we are happy to provide those to any customer who requires them. Best uses for WAM. So this is a neat chart. So across the top, you have a value lever. This is something that gets talked about a lot. Why do you want to use wire arc additive manufacturing? Reduce lead time. We can do large items. So when you're looking at castings, when you're looking at forgings, we had a couple conversations with some folks that stopped by our booth earlier that they're looking to replace castings because the lead time right now is 6 to 9 months. Well, this is something that we can probably help you with and get it done for in weeks. Reduce material waste. When you're starting with a casting, or if you don't have that option and you have to buy a large forging or a block, you have a ton of chip removal. Now, chip removal translates into machine hours. Machine hours translate into cost. So by additively manufacturing and getting closer towards your near net shape, we can save you money on that. Reduce tooling and fabrication costs. Again, for some of the larger complex tools with a face sheet that has a lot of rise and run in it, or it's got multi-contoured, you're looking at breaking the face sheet up, you're looking at chip forms, bump chips, manually manipulating that, a lot of weld seams that go into that, heat treat, anneal cycles. There's just a lot of other costs that's not looked at. Simplifying joining, tubular connections, multiple joints or weldments. It's a lot easier when we can plan for it in an additive state to join the pieces together. Enhanced performance, lightweight. Looking back at that propeller, we were able to print that hollow. So you can reduce weight along the way as well. Use cases, rapid prototyping. I know our additive team worked pretty hard on this one. Customer came to them, they were looking to replace steel castings. It was 6 months just to get the first casting done, and then after that they had 3 months of revisions. And then typically after those 3 design iterations, you're gonna change it at least 3 times. You're looking at 12 months to manufacture, get that casting correct to move forward. Now 3D printing that, we were able to get this done in less than a week for them, and that was their first iteration. So think about what you can do and how you can change the way you do business, the way you manufacture, when you have that much more time back in your schedule. Additional use cases, these are some other great ones for oil and gas. Left-hand side, we've got some low-carbon steel. These were replacement parts as well. In the center, this mixer blade. So this was for some very old machinery. So this was about 5.5 feet tall, and there's actually cooling channels that run through the center of that. So that was a neat reverse engineering that we did. And then on the far right-hand side, you can see this is us pushing that 8,000 pound and 8 feet tall limit with a round tubular cylinder that was just printed from the base up. This, I believe, also headed down to Texas for some additional testing to look at tensile strength and see, where the breaking point of that is, and everything is just as if it was an extruded piece of steel. Fast turnaround versus castings. I talked about this a little bit. Typically, when you go through castings, you're going to go through a planning, a preliminary design phase. You're going to have a solid model of molds, and you'll have that time. Then you're going to go through a few iterations and simulations. You're going to go back and forth and back and forth. You're going to find some that come to you and say, oh, I didn't put enough stock on here. I need a new one now. Now, when you compare that again to down at the bottom, the design, build, validate, and wire arc additive, we are within 12 weeks, where previously you're looking at 10 months. I mean, that time right there is enormous, especially when sometimes we have cases where customers are actually bidding on projects for their end user, and they need to make up time, which we see in the aerospace industry. They typically agree to a date, and then they try to back into it, and you have almost no time to get anything done. Casting conversion, this gets asked a lot as well. When you're looking at the cost savings for material, we have on the left-hand side of the chart, you've got high value material. That's going to be your Inconel, that's going to be your Invars, stuff like that. Right-hand side of the chart, your lower value material, that's going to be your mild steels. What we're seeing is, as you go through the material, you're going to see a drop in material cost. You're certainly going to see a drop in labor. And then the overall cost, you're going to see a decrease in about 23% on higher value material, which this is something that we've actually already gotten feedback from our customers on as well for aerospace tooling. And then the lower value material, like the mild steel, that's something that when you're trying to do prototype tooling, prototype parts, that's something we can turn around extremely cheap. We're very, very competitive on, and you can get that part into your hands for testing much, much faster. Obsolete legacy parts. So use cases, again, this is something where we've had to take parts that were previously made, they don't have replacements for, we've had to scan them, reverse engineer them, and create a CAD model out of them. From that, we've been able to generate our additive model, and then we've been able to machine it. So again, by doing this process, we've been able to support legacy part replacements or programs that those parts became obsolete, and they were able to continue and not have to go through an entire tooling revamp or redesign. Quick turn replacement parts, again, another one. We have Chevron up here. I know we've done a whole lot for them as far as producing parts in a quick manner. We actually delivered 8 production components in 30 days. 8 nickel alloy piping and fitting components. They were extremely happy with what we were able to give to them, and that was over 5,000 pounds of nickel wire. So 5,000 pounds in parts in 30 days. They came to us and they had asked, hey, we have a 2 to 3 month lead time for machine forgings, and that's going to be a very common thing that we're seeing nowadays. They were risking shutdown for weeks. And that's just what their initial risk assessment was by not having these parts, was it's going to affect us by at least a few weeks. What that trickle effect is going to do to the rest of production or everybody else that's involved, you probably can't even look at it up front, but you knew that you needed replacement parts as quick as possible. So our additive team was able to get these designed, print them within 24 hours, and have parts, the first parts back to them within a week. Tooling for aerospace composites. In just the past year, in the past 3 years, we've delivered several different aerospace toolings that are steel, that are Invar. I think we've got a couple dozen going through the shop right now. The first ever one that we did was actually for, it's now ST Engineering, previously Middle River, GE, but it's now owned by ST Engineering. This was approximately 6 feet long, over 1,500 parts, and this was Invar. After going through about 6 to 9 months of testing, it went into production, and after 2 years of our customer using this, the thermal profile still holds up, dimensional stability and vacuum integrity are all still good. Boeing, this was one that we were pretty proud of as well. This was Boeing and the WISC program. So it was a really cool collaborative design effort between the BR&T program and our additive and Baker teams. So the tool itself was about 10 feet long. This one we got to take a different approach where we not only print face sheet, but we also included the substructure underneath as well. So we actually were able to print 2 halves of this, about 5 feet tall. So we're able to ramp up the speed of this. Then we joined them in the center, conventionally welded them, and then we machined the part out, or the tool out. So everything we've heard back from them on this, they're extremely happy, and they're looking forward to using more of these tools in the future with us. General Atomics, this was another one that they had come with us. and they wanted to look at additive as an option for some of the tooling they have coming out. They wanted to look at what the cost savings are going to be. They want to look at the lead time as well. So on this project alone, we were able to save them 30 to 40% and also drop their lead time about 20 to 30 by going the additive route compared to the conventional route. So it's vacuum tight, uniform thermal survey, and exceeds target GD&T with some of the feedback that we've got from them. And it's beginning to undergo some of its cycle testing now, but it's going to hit 200 cycles. TKY joints, this is pretty common for oil and gas. This was kind of a neat project as well. We partnered with Ohio State University. Again, this is something that these guys are trying to weld in the field, out in the oceans. This makes it a much, much simpler solution. They were also able to look at some of the structural FEM cases for it and look at what those, how those interact with one another as well. And that's where OSU came in. They utilized their topology optimization software, and we knocked it out of the park with that. Print solid or hollow. So this is a great example. Again, there's another one of those joints there. Some more examples of that being printed on the positioner table. And here's another really neat video of the positioner actually in action while it holds in 1G while the torch runs around and lays down wire. Again, this is one that kind of came out of the blue that we hadn't thought of, but sculptures and structures. We've looked at the oil and gas. We've seen some of the structural benefits to it, but this was a really, really neat project. It was called Convergence by the Jenny Saban Studio, and this is over in the University of Nebraska. It's the medical center. So if anybody has a chance, swing by, check that out. This is 28 feet tall and 12 feet in diameter. Anyone that's interested in seeing more pictures of it, swing by our booth. We're right outside the doors, 433-163. Our marketing guy, Sean, has some pictures of it actually being trucked in, and it's just enormous coming down the street. So we printed this in 9 different sections, shipped to Omaha. They assembled it there, and then they actually put iridescent panels all on the outside. So as you walk around it and the sun hits it, it changes colors. So it's really neat. And being that it's outside of the medical center, that's actually a heart valve. So that's what that shape is. That's all I've got.